What do Sydney Opera House, Soviet apartment blocks and Roman aqueducts have in common? They're all built with a technology that's been forgotten, vilified and reborn more times than any other building material in history. Today we are uncovering the remarkable story of precast concrete facades, a tale of innovation, disaster and ultimate redemption that spans over 2,000 years. My name is Eugene Korch. I'm practicing facade engineer and I teach facade engineering at the Institute for Architectural Science and Technology. Today we are diving deep into precast concrete facades, how they have shaped our cities, why they fell from grace, and how they are quietly revolutionizing modern construction. Our story begins in ancient Rome with Opus Caementicum, the Roman concrete, the world's first hydraulic cement. The Romans didn't just invent concrete. They have invented the idea that stone could be artificial, poured into any form and set into something stronger than nature provided. The Pantheon's massive dome stands as a proof of concept. Built nearly 2,000 years ago, it demonstrated concrete's structural and sculptural potential. This marked the beginning of concrete's paradoxical history. The same material would create both the most extravagant architectural forms and the most austere social housing. But here's what's fascinating. Despite this early Roman invention, the technology was essentially lost for over 1,000 years. In 1756, John Smeaton faced a challenge: rebuilding Eddystone lighthouse in conditions where traditional mortar would fail. His solution was hydraulic lime, what we now call Portland cement. This single innovation gave us the most widely used material in the world today. By the 1770s, Eleanor Coade and her daughter were manufacturing Coade stone, molded ceramic blocks that could replicate expensive carved stone details. Suddenly, ornate decoration that once required master's craftsmen could be mass-produced. Leading architects like Robert Adams and John Nash embraced this artificial stone with enthusiasm. However, at the time, the precast fabricated stone was used purely as ornament and not because of its structural properties. In 1905, something remarkable happened in Liverpool. John Alexander Brodie, an engineer who also invented the football net, constructed the Eldon Street apartments using prefabricated concrete slabs. This was one of the first comprehensive precast concrete buildings in history. Think about that for a moment. The same mind that gave us the football net also pioneered industrial housing. Both solutions were so elegant, so obvious in hindsight that we barely think about them today. Similar buildings began appearing across Western Europe in the 1920s. This footage from Frankfurt am Main in 1927 shows development by German architect Ernst May. Remember this name? We will have to come back to him later. All these early buildings used precast concrete as load-bearing external walls, following thousands of years of construction tradition where facades carried the building weight. Then came World War I. And everything changed. The in-situ reinforced concrete frame revolutionized construction. Suddenly, external walls didn't need to bear loads. They could be light, fast to install and decorative. In-situ concrete seemed quick enough. Curtain walls were the future. Even modernist pioneers like Walter Gropius and Mies van der Rohe ignored precast entirely. Le Corbusier used precast only as an embellishment, balustrades, solar shading and decorative veneers. He embraced precast as main material just once, much later in his career. The 1958 Philips Pavilion in Brussels, designed with Yannis Xenakis as a system of ruled surfaces creating large irregular geometries from single precast shapes. This pavilion's importance cannot be overstated. Built over 50 years before architectural computer-aided design or CAD, decades before parametric design tools, it achieved what we'd now call a computational architecture using pure geometric thinking. Ironically, the same year saw another precast revolution. In 1958, the same year, engineer Vitaly Lagutenko completed the first K7 block in the Soviet Union, the iconic Khrushchevka building. Nikita Khrushchev, the first Secretary of State, had declared that every Soviet family deserved housing. The construction industry had 7 years to deliver 15 million homes. The challenges were the lack of skilled workers and time. And the solution was industrial-scale precast concrete production. Concrete panels shaped like waffles rolled off production lines resembling automotive assembly lines. Entire districts, complete with schools, kindergartens and cinemas, rose from these standardized components. As Khrushchev declared, we are not against beauty, we are against excessiveness. No decoration, no ornament, just pure industrial modernism. These concrete boxes sprouted across the Soviet Union and Eastern Bloc like architectural mushrooms. The construction speed was breathtaking. Entire 5-story buildings erected just in 1 week, complete fit-out finished in under a month. When you build that fast, quality inevitably suffers. These buildings had no insulation. With winter's temperatures hitting minus 30 degrees Celsius, residents called them concrete refrigerators. Acoustic performance was equally poor. Internal walls were just 60 to 80 mm thick, enough for structure and fire safety, but not for privacy. In communist countries, privacy from neighbors or secret services wasn't exactly a priority. Despite the quality issues, the housing crisis was solved. By the end of the Khrushchev era, 54 million people lived in prefabricated panel buildings. Imagine nearly a whole population of modern UK to be rehoused within just 11 years and 37 days, and he was still not happy about the speed. Of course, the corners were cut. Meanwhile, in 1957, Danish architect Jørgen Utzon employed precast concrete panels with cast-in tiles in Sydney Opera House. Due to the building's complex geometry and the fact that the construction began without complete working drawings, the project ran massively over budget and took a decade to complete. Compare this to 15 million Soviet apartments built in the same time frame. Yet the results were stunning, one of the greatest architectural achievements of the modern era. Unlike the deteriorating panel buildings in Eastern Europe, the Opera House still looks modern and relevant today. Precast concrete became the solution for housing crisis on both sides of the Iron Curtain. The Berlin Wall itself was largely precast concrete. Entire towns rose from precast panels. Marzahn near Berlin in the east and Gartenstadt war in Bremen in the west, designed by our old friend Ernst May. He would spend the next 2 decades designing thousands of prefabricated apartments in West Germany. He nearly realized Le Corbusier's vision for Paris in Wiesbaden, proposing to demolish the historic old town and replace it with efficient modernist prefabricated boxes. Fortunately, residents opposed this plan. May believed standardized apartments would create new communities, but neighbors in these buildings rarely knew each other. The anonymity was so complete that these buildings became perfect safe houses for radical terrorist organizations. Post-war Britain faced its own housing crisis. The government's answer was to increase buildings' productivity through prefabrication.
The only answer is more houses. The government are looking to increasing the productivity in the building industry.
Sounds familiar, right? The Ronan Point Tower, using the Large Panel System, or LPS, opened in March 1968. 2 months later, a gas explosion on the 18th floor blew out an external wall. The progressive collapse that followed killed 4 people and injured 17. An investigation revealed shocking workmanship failures.
The engineers hacked back the concrete and found in flat after flat that the metal bars meant to hold the panels onto the building were just not there. What proportion of bolts were missing and what proportion were put in?
I would say about 80% were missing and about 20% put in.
Public confidence in load-bearing precast construction was destroyed. One resident's words captured the mood.
If they offer you another flat, will you go in one?
Oh, no, thank you very much.
Anything like that anymore.
Not that silly.
No.
Load-bearing precast was largely abandoned in the UK housing, but it would return in a different form, as cladding material. But more on that later. Early post-war housing prioritized speed and standardization over thermal performance. Those Soviet Khrushchevkas had no insulation, just bare concrete, earning them the nickname concrete refrigerators. By the early 1960s, Scandinavian engineers pioneered the insulated sandwich panels. Mineral wool, sandwiched between 2 concrete leaves, marked a turning point in facade design. The Soviet Union adopted similar approaches with mineral wool or expanded polystyrene. While the insulation thickness remained minimal, often just 30 to 50 millimeters, these early sandwich panels set the stage for modern energy-conscious systems. Today, precast sandwich panels feature minimum 150 millimeter insulation layers between structural and facing walls. The 1980s brought postmodernism. The precast concrete ability to take any shape made it perfect for outlandish new designs. The best example is Ricardo's Bofill social housing in Paris, using the material associated with brutalism to create something entirely different. But Bofill wasn't using precast for speed or mass production, only for the complex shape it enabled. His buildings used in situ concrete structure, with precast panels inserted into frames' apertures, creating decorative facades. This wasn't entirely new. Back in the UK, engineers had developed hybrid systems to address Ronan Point's progressive collapse issues while offering more generous apartments layout. The most famous example is Grenfell Tower, built with in-situ reinforced concrete structure and precast concrete cladding panels. These panels rested on the in-situ slabs with no thermal breaks. They were purely decorative, uninsulated. Once again, concrete served mainly as a decoration. Both modernist and postmodernist precast developments became associated with failed social programs. Both those buildings in Paris became so synonymous with dystopia that they served as backdrops for films like Brazil and The Hunger Games. Low-quality housing made concrete blocks synonymous with mass-produced mediocrity. Exuberant postmodernist ornamentation hardly helped with this reputation. When the time came to address thermal performance issues in existing precast buildings, the industry faced two choices: internal or external insulation. Internal insulation would intrude on residents' living space and create interstitial condensation problems. Installing insulation internally without decanting the apartments is hardly possible, and the apartments themselves will be slightly smaller at the end of the exercise, as the insulation will eat in the existing space of the apartments. Worse still, thermal bridges at the slab-to-panel connections would remain unresolved. The thermal bridges will not be dealt with at these locations. External insulation proved to be far more effective, wrapping building in insulation and rain screen cladding with ventilated cavities to manage moisture. It was also less intrusive for residents. As exposed concrete towers fell from grace, architects were happy to cover what many saw as ugly, soulless concrete. This is exactly what happened at Grenfell Tower from 2014 to 2016. To save money, designers chose combustible aluminium composite cladding, or ACM, insulated with high-performance insulation, which was also combustible. Just over a year after completion, 72 people lost their lives in the resulting fire. The morning after Grenfell fire, only the precast concrete structure remained intact, stained but undamaged, while the cladding and insulation had completely burned away. The industry was forced to give precast concrete another chance. The mass housing era seemed over. Residents demanded larger apartments with flexible layouts that exceeded what Khrushchevkas could offer. But developers still wanted prefabrication's speed and cost efficiency. Post-Grenfell, rain-screen facades fell from grace. Metal panel cladding became associated with cheap, low-quality construction. Precast concrete facades found new fashion in so-called window panel systems. The primary structure remained in-situ reinforced concrete, but facades are prefabricated off-site with windows pre-installed in the openings and craned into position. This time, panels connected to the slabs through stainless steel brackets or hung from the columns and shear walls. The most common installation strategy is two stainless steel brackets at the bottom of the panel, transferring the dead load to the slab, with two or more lateral brackets with vertical slots in them at the top of the panel, transferring the wind load back to the slabs or columns, while allowing the panel to accommodate deflection and movement of the primary framework of the building. Gaps between the slabs and panels serve as thermal breaks, eliminating notorious thermal bridges. The gap between the slab and the panel is also needed for installation tolerances and filled with compressed mineral wool fire stops, preventing flame and smoke propagation. Mineral wool insulation is installed behind panels and covered with stud walls and painted gypsum boards. Smart vapor control membranes positioned between the stud walls and the gypsum boards respond to relative humidity, normally vapor closed but opening when relative humidity levels rise, allowing trapped vapor to escape. This addressed the interstitial condensation issues that plagued earlier systems. External concrete panels are at least 150 mm thick, with about 200 mm mineral wool insulation behind them, covered in at least 12 mm gypsum boards. They offer fantastic sound insulation. The joints between the panels adopt two-stage seal strategy similar to the curtain walls. But unlike curtain wall facades, the seals are executed with silicon rather than rubber gaskets. There are weep holes in the outer silicon seal, either in vertical or horizontal, allowing any moisture to escape, with the inner seal serving as ultimate water and air barrier. Precast has yet another superpower up its sleeve, which enabled widespread adoption in the recent decades. Other materials can be cast into its surface. With skilled labor shortages now critical, precast concrete addresses this challenge elegantly. Thin brick slips with dovetail keys at the back can be cast into panel surfaces off-site, enabling high-rise brick buildings at speed and cost impossible with traditional masonry. This method also liberates designers from traditional brick bonding constraints. Since bricks aren't stacked but cast into surfaces, virtually any pattern becomes possible at no additional cost. Stone and terracotta are equally popular choices, creating buildings that appear traditionally crafted while being industrially produced. The only giveaway of these facades' panelized nature are the joints between panels. These panels reach up to 12 meters in length and at least 1 floor in height. They are only limited by the size of the lorry or a truck that can deliver them to site. Precast panels achieve high prefabrication tolerances but still require minimum 5 mm tolerances per panel. And just like curtain walls or unitized facades, these panels have to accommodate the building movement and slab deflection. Combined with building movement and installation tolerances, joints are rarely less than 15 mm for smaller panels, with standard precast concrete facade joints to be 25 mm between the panels. These joints remain highly visible next to 10 mm mortar joints between cast-in brick slips, even when silicon color matches mortar, or even if the silicon is dusted with crushed dry mortar. Architects try to design decorative protrusions and recesses next to the joint locations, making them less visible. And more recently, we see engineering solutions when some of the bricks being left out in the joint locations and later installed in situ once the panels are in place. These brick slips bridge between two panels, completely hiding the joint. However, this only works with smaller panels and requires the highest level of workmanship and engineering, reserved for very expensive, high-profile projects. Glass fiber reinforced concrete, or GFRC, deserves special mention. With digital parametric tools making complex shapes easy to model, a new architectural style, parametricism, emerged in the early 21st century. Structures like the Le Corbusier's 1958 Phillips Pavilion became fashionable again. Concrete made it possible, but this time the expectations for buildings' envelope performance were higher, not just structurally sound, but thermally efficient and watertight. Rain screen assemblies with insulated and ventilated cavities are perceived to be the best at these tasks. Since these shapes no longer needed to be load-bearing, concrete panels could be as thin as possible. GFRC panels, reinforced with glass fibers instead of steel, can be just 1 inch thick while taking any shape. This material appeared on virtually every parametric building in the first 2 decades of this century. Unfortunately, GFRC stains easily, making many of these structures look outdated within a decade of completion. Today, the world faces another housing crisis. The answer remains the same: build more houses. Some level of prefabrication is expected on virtually all developments, ideally with both structure and facade prefabricated simultaneously. Only one construction type can deliver both: load-bearing precast concrete shell and core systems. But this time it is different. These structures must solve all previous issues while meeting entirely different quality, performance, and comfort expectations. They're designed for larger apartments with flexible room layouts, utilizing not just panels but precast columns, steel beams, and elaborate transfer structures. Minimum 150 mm insulation separates structural and decorative leaves. Most of the times, insulation is even thicker. These precast concrete sandwich panels offer the best acoustic performance due to the sheer mass of both concrete leaves, further enhanced by a layer of mineral wool insulation between them. Connections between panels and slabs prevent progressive collapse. If one panel fails, the rest remain in place. The world's tallest prefabricated structure is built that way. This breed of structure in facade evolved so much you can't even tell that this is precast concrete panel building. The outer concrete leaf can be covered in brick, stone, or terracotta. Not only finishes can be cast in these panels, balconies can be attached through the brackets cast into the panels off-site. Entire neighborhoods use these systems in London and Northern Europe. The most famous is City Island development in Canning Town in London. An entire town built on an island with thousands of homes in blocks ranging from 8 to 26 stories, all constructed in less than 10 years. No one realizes these are precast concrete buildings. They all appear to be brick structures with balconies and large windows. No other material or system can achieve these results at that speed. One challenge remains for concrete: carbon footprint. Concrete is unfortunately the least carbon efficient material, requiring more innovation. Perhaps hybrid approaches will provide solutions: cross-laminated timber as partitions or slab infills, or advancement in aggregate technology. This is an engineering problem left for precast concrete to solve. From Roman temples to Soviet housing blocks, from architectural disasters to modern redemption, precast concrete facades tell a story of human ingenuity adapting to changing needs. Today, as we face new housing crisis and sustainability challenges, precast concrete continues evolving, hiding in plain sight behind brick veneers, enabling architects' ambitions and quietly revolutionizing how we build. The next time you see a high-rise brick building rising faster than seems possible, remember, you're probably watching the latest chapter in the 2,000-year story of innovation. If you found this story interesting, subscribe to our channel for more facade engineering content, from curtain wall to rain screen system to insulated render assemblies. Want to dive deeper into facade engineering or become a facade engineer? Check out our courses and qualifications at the Institute for Architectural Science and Technology. We offer many free courses to explore. All 3D models and drawings from this video are available on the Facade Intelligence platform. Make sure to subscribe to a free plan. Thanks for watching, and we will see you in the next video.